All right, today we are pulling back the curtain on the AI that is literally changing everything. We're going to jump in and demystify how a large language model, the engine behind things like ChatGPT, actually does what it does. We're talking about the real mechanics behind the magic. So let's get into it.
We've all been there, right? You type in a question and what comes back is, well, it's so good, so creative that you just have to stop for a second. It honestly feels like there's a real intelligence on the other side. It's that moment of awe that makes you wonder.
I mean, what is really happening behind that blinking cursor? Is it some kind of magic trick, a new form of consciousness, or is it something else? Well, today we are going to pry open that black box and see for ourselves. Okay, so to crack this thing open, you first have to understand that pretty much all AI models, from the simplest ones to these huge language models, are all built on the same basic idea. And you can actually boil it all down to a surprisingly simple formula. And this is it. This is basically the master key to all of AI. You give it an X, your input, your question. The model then uses its architecture, F, and a bunch of numbers called weights, W, to spit out a Y, your output, the answer. Now, that formula looks simple, but all the power, all the mystery, it's all packed into F and W.
So let's split those two things apart. On one side, you've got F, the architecture. Think of this as the blueprint. It's just code designed by human researchers, and we understand it completely. But on the other side, you've got W, the weights. And this is the secret sauce. It's just billions and billions of numbers that the model learns from data. They aren't designed, they're discovered. And this, right here, is where all the magic and the mystery of AI really comes from. So what is this architecture, this FI, anyway? Well, it's not one single giant function. It's actually much simpler. It's a whole bunch of layers stacked one on top of the other. Your data goes in the top, gets processed, and the output of that first layer becomes the input for the second, and so on all the way down. This layered setup is why you always hear them called neural networks. Okay, so we've got this stack of layers, and it's processing our question. But how on earth does that turn into poetry or computer code or a complex essay? Well, the answer is the biggest secret of them all, and it is shockingly simple. That's it. No, really, that is the entire trick. For all of their incredible power, these huge, complex models are really just doing one thing over and over and over again. They are predicting the next word. All of that amazing complexity you see, it all emerges from this one simple repeated loop. And this is a perfect look at how that loop works. The model takes our first few words, what is fear of, and it predicts just one word, long. Then, and this is the clever part, it tacks that word onto the end of the input, creating a new sentence, and feeds it right back into itself to predict the next word, words. And this loop just keeps going, one word at a time, until the model finally predicts a special token that basically says, okay, I'm done. Okay, but wait a minute. Computers don't understand words like fear or long. They're machines. They only get numbers. So how does the model actually do any of this? It needs some kind of translator to turn our language into its language. And that's the next critical piece of this puzzle. The entire process relies on this two-way translation. First, your prompt, your text, has to be turned into a long string of numbers that the computer can work with. And then, after all the math is done, the final numbers have to be translated back into the words that you end up reading. So, this translation happens in 3 quick steps. First, your sentence gets chopped up into little pieces called tokens. Then, each of those tokens gets a unique ID number from a huge vocabulary list. But right now, these are just meaningless labels. That brings us to the final and honestly the most important step, embedding. This is where the real magic happens. The embedding process takes that simple ID number and turns it into a long, rich list of numbers, a vector that actually represents the word's meaning. It's like placing the word on a giant map of concepts where words with similar meanings, like king and queen or running and jogging, end up really close together. This is how the model begins to understand relationships. All right, so the model's taken our input and turned it into meaningful numbers. It's run all those numbers through its stack of layers. But then what? How does it choose that single next word from a vocabulary of tens of thousands of different options?
The answer is something called logits. So at the very end of the process, the model's final layer spits out a raw score, a logit, for every single word it knows. You can think of this like the model's internal ranking system. A higher logit score means the model thinks that word is a better bet for what should come next.
These logits then get turned into simple probabilities. But here's what's so cool. The model doesn't just pick the word with the highest score every single time. Instead, it kind of rolls the dice. It samples from these top options. So yeah, the might have the highest chance, but there's still a pretty good chance it picks fear or A instead. And that element of randomness is exactly why you get a slightly different answer every time you ask it the same question.
So now we get it, right? We understand the theory, from the layers and the weights all the way to the logits and probabilities. So let's put that knowledge to the test. Let's see if we can control the model's output by performing a little surgery on its internal process. Okay, here's the challenge. We're going to ask the llama model for a haiku. Simple enough, but there's a huge catch. It cannot use the letter E. That's the most common letter in the entire English language. Let's see what happens when we just ask it nicely. And it failed. It tried so hard, but right at the very end, it couldn't help itself. The word gentle snuck in. So just asking the model to follow the rule, that wasn't enough. To really enforce it, we have to go inside.
But because we know about logits, we can do exactly that. We're not just a user anymore. We can be a surgeon. We can go right into the model's decision-making process and directly mess with the scores it's generating.
And here's how the surgery works. Step 1. We make a list of every single word in the model's vocabulary that has the letter E in it. Step 2. As the model is about to pick a word, we intercept its logit scores. Step 3. We find the scores for all those E words and just overwrite them with negative infinity. What that does is it slams their probability down to absolute 0. It makes it impossible for the model to choose them. And look at that! By getting our hands dirty and directly controlling the logits, we get a perfect haiku with no E's. A warm sun on sand, a big sky so vast and blue, a hot, long, fun day. It's a total success. We didn't just ask it, we went inside and forced it to obey our rule.
Oh, and here's a hilarious little detail. Our very first try at this surgery actually created an endless loop. The model just wouldn't stop writing. You know why? Because the special end token that tells the model it's finished, it also had the letter E in it. By banning it, we accidentally made it impossible for the model to stop itself. It's a perfect reminder of how literal and how not magical this whole process really is. So we did it. We opened the black box. We've seen the layers, the weights, that one word at a time loop, and the logits that guide it. We've even performed surgery on its brain. Which brings us to the biggest question of all. Is this machine really thinking the way we do? Or have we just built the world's most sophisticated, most convincing prediction machine? That's definitely something to think about.